This is the 130th Hot Science School Talk. I'm very pleased to introduce tonight's speaker, Peter Stone. He's a professor of computer science and executive director of Sony America Artificial Intelligence. He got his degrees from Carnegie Mellon University and the University of Chicago. And the thing about Peter is, I want to share with you what we can do generally with artificial intelligence, and then the kinds of things that Peter does. So, one can use artificial intelligence to make a robot tighten the lug nut on a car in the Tesla Gigafactory. And that's pretty cool to get a robot to do that. What Peter's group does, the research group that he leads, is probably best exemplified by this quote from his website. It sums it up to me. It's, quote, "The goal is to make a robot do something as part of a team operating in real-time, noisy environments in the presence of both teammates and adversaries." Wow, that's much cooler. Peter's developed teams of robot soccer agents that have won the Robo Cup, which is the equivalent of the World Cup of soccer, but for robots who are playing soccer. Yeah. So those of you who are up on your Dr. Stone trivia, do you remember what year it was that his team won the Robo Cup? Anybody remember? Like you would know. It was 1998 and 1999, 2003, 2005, 2011, 12, 14, 15, 16, 17, 19, 21. So Peter, what happened in 2018? Second place. Okay. Wow. So Peter Stone, let me read you some of his accolades. He's a Sloan Research Fellow, a Guggenheim Fellow, a AAA Fellow, an IEEE Fellow, a AAAS Fellow, an ACM Fellow, and a Fulbright Scholar. He's a member of UT's Academy of Distinguished Teachers, and there are many other awards, but hopefully you all can appreciate that tonight we are hearing from the top expert on artificial intelligence. Like me, Peter is born and raised in New York. Unlike me, Peter graduated as valedictorian from Amherst Central High School, where he was also co-captain of the soccer team. And while in high school, he performed violin on several international concert tours with the Buffalo Suzuki Strings, including as a soloist in Russia and in Hungary. Okay, that's enough. I'm convinced Dr. Stone is a robot. Please welcome Peter Stone.
All right, thanks, Jay. Thanks, all of you, for being here. Welcome to the Year of AI at UT Austin. In fact, there's a lot of exciting things going on here at UT. We have, I'm in the computer science department, as Jay said. We were awarded one of the first AI institutes by the National Science Foundation. This is led by Adam Clivens, the Institute for Foundations of Machine Learning. I'm a founding member of a campus-wide initiative called Good Systems, which is our sort of AI for Good initiative, which involves people from many different disciplines, including computer science and engineering, but also social science and public policy. I'll talk a little bit about that at the end of the talk. This was inspired by an effort I've been involved in for many years called the 100-Year Study on Artificial Intelligence. And for those of you who are new to the field, I highly recommend going to that website and reading the reports there as a sort of gentle introduction to where the field is. And I'm the director of Texas Robotics. I hope a lot of you got to go over and see our facilities in across the street in Anahis Gym. This is what it looked like before we filled it up with robots. But you got to, how many of you went across the street and saw some of the robots? Good, a lot of you, great. So, so we tried to set that up so that you could always go through there. You can see through the windows to what the labs, it's sort of end of the day on a Friday, so it wasn't that busy right now. But if you come back during the week, you'll see robots moving around and the students there doing their thing. So I think there's a number of big scientific questions of our time. I think there's three that really stand out. One of them is, how did the universe originate? And so people think about this in the physics department and in astrophysics and in astronomy. How did life on Earth originate? That's the purview of biology. The biologists are thinking about that a lot. And then the third, the one that captivates me, is what is the nature of intelligence? What is this thing we have brains in our heads, they allow us to be intelligent. How does that work? And so if we're going to get at the question, the nature of intelligence, there's a number of different ways we could approach this problem. We could, we could study it by thinking about it. What does it mean to be intelligent? Is a person intelligent? Is a dog intelligent? Are you intelligent based on what you do, or does it matter how you do it? That's sort of the nature of you can think about that through the field of philosophy. We could also get at the nature of intelligence by studying human or other animal behavior, and sort of watching things that we consider being that are intelligent, and trying to figure out how they're working, or what it is that they're doing that characterizes intelligence. Psychologists think about that. We could study human or other animal brains and try to look inside and see what's going on when when there's neurotransmitters that are governing the synapses in the brain, and what happens when light comes in through your eyes and you form a perception of something. That's what neuroscience is about. Or we could try to build and analyze intelligent artifacts and try to use that as a way to understand intelligence. All of these are valid ways of getting at this really huge scientific question. But I'm going to, tonight, as I'm talking with you, I'm going to be taking this last perspective, trying to think about if we are what can we learn about intelligence by building and analyzing intelligent artifacts? And that's the purview of computer science, of artificial intelligence. And an analogy that's often used is that that this would be a way of it's sort of the same thing that if we're trying to study flight, you could look at birds and try to mimic birds, or you could try to build an airplane that flies a little differently than birds, but still flies. And the Bernoulli principle still holds, and there's sort of general principles we can learn about flight by trying to build things that fly, even if we don't mimic exactly the way it's done in nature. So from that perspective, one of the goals of artificial intelligence and robotics, it's not everybody's goal in the field, but for me and colleagues like me, is to try to build fully autonomous agents in the real world. In some sense, building things that do things that we would consider intelligent if a person did. Building machines, building robots, or building software programs. And then the question is, how would you go about doing this? And there's you could start by by just working on the components, on working on how do you do vision, or how do you do motion, or how do you do planning. Or you could try to go from more the top down and try to build complete agents to perform increasingly complex tasks. And I think both paradigms are important. I'm going to be talking tonight sort of more from this second paradigm of let's try to build complete agents that can sense, decide, and act in a closed loop. What do I mean by a closed loop? I mean that there doesn't have to be a person involved, that the machine is going to have some way of perceiving what the state of the world is right now, have some process for deciding what actions to take those actions, and then that'll affect what perceptions it gets next, and it just continues on in the same way that we do, or similarly to the way we do. And then this can drive research on the component algorithms and the theory, and I'm going to talk especially, or my research focuses especially on two components of intelligence. One is learning. An autonomous agent is something that I think an intelligent autonomous agent is something that improves its performance over time based on experience. And so that's the sub-area of AI called machine learning. And I also focus a lot on interaction among autonomous agents. If you have an autonomous car and it pulls out of the driveway, it's not going to be driving by itself on the road. It's going to have to interact with other cars. And that's sort of what we think about in multi-agent systems. And so this sort of top-down building complete intelligent agents perspective has the mantra of good problems produce good science. If you can come up with good challenges, then it's going to drive you to make innovations that will improve our understanding of how to build intelligent artifacts, and through that to understand the nature of intelligence. So with that motivation in mind, I can give sort of a 1-slide overview of the research that I do in my lab here at UT Austin This is a sort of a research question that's driven my whole career. I've been putting this question up on the talks that I've given ever since my PhD thesis back in the late 1990s. And it's, to what degree can autonomous intelligent agents learn in the presence of teammates and or adversaries in real-time dynamic domains? So there's a little jargon here. You might not understand all the words yet, but I hope by the end of tonight this will all make sense. And within artificial intelligence, there's sort of sub-areas that we then end up focusing on or publishing in the academic world. There's a community that works on autonomous agents that sense, decide, and act. Multi-agent systems, robotics is an area. And also, especially, and what I'm going to focus on a lot in today's talk, is machine learning, and in particular, a type of machine learning known as reinforcement learning. And if there's one sort of area of expertise that you're going to walk away with after tonight that you're going to have more knowledge of than before you came in, it's going to be in what is in this area of reinforcement learning, and how does it work, and what is it? So as I said, there's sort of, you can do research in building intelligent agents, both on the sort of bottom up, working on new algorithms or for perception, decision making, or action, new theoretical results. And I do a bunch of that in my lab. There's papers that we publish in conferences that are sort of on this, sort of what can we do, how can we improve existing algorithms. But when I give a one-slide introduction to my lab like this, it's a lot easier to talk about the more top-down approaches, the challenge problems that inspire the research that we do. And so, as Jay said, I've been involved in the robot soccer competitions for many years. This is from almost 20 years ago now. Some of the old Sony Aibo robots playing soccer. And there it is, one of our robots scoring a goal. And you have to remember that there's no remote control here. That robot was using a camera to see where the ball was deciding when it should pass and when it should kick, and then was actually executing those actions several times a second. Then those robots got retired, and then we started using these humanoid robots. And so I'll show you what RoboCup looks like now. So this is a video from a competition that happened several years ago, where our robots are the ones with the pink waistbands and their arms behind their back. We were playing against a team from the University of Bremen in Germany. Here you'll see our robot going in on a breakaway. And calmly, again, we're on the sidelines. We can't do anything. We programmed them beforehand, but we can't really help the robot. They have to decide, how to work as a team. And here you'll see calmly bank the ball off the goalpost and in. So we went on to win that game 4-2, and when we came back to campus, they lit the tower orange for us, which was quite an honor. And so this is sort of an example. If you're going to build robot soccer playing agents, they have teammates. Each one is deciding for itself what to do. They have adversaries, the opponents, that are going to play different and unexpectedly. You don't know what they're going to do ahead of time. It's real time, it's dynamic, it's all those words I showed you that are up there. They're agents, and we use machine learning to try to improve their performance. And so that's one domain. I'll talk a little bit more about robot soccer or RoboCup in the coming slides. Another sort of domain that inspires me is trying to create general purpose service robots. So often if you go to Anahis Gym across the street, you'll see a robot like this one just wandering the hallways. You don't have to ask us for a demo. We try to have it on most of the time. And this particular video was joint research with a colleague of mine, Ray Mooney, on grounded language learning, trying to get robots to be able to understand spoken language. This was before the days of ChatGPT. We now are combining them with large language models. But the goal is to have these robots just be a part of the environment, to be able to be in our office buildings or be in our homes, to be able to be general purpose helpers, to know when you want to be helped, to know when you want to be ignored, to know when you want to be entertained, to be able to navigate through crowded spaces in a what we call social navigation. There's all kinds of problems that are motivated by these general purpose service robots. And then, like many others, I've been inspired a lot by the domain of autonomous driving. I had a car in the DARPA Urban Challenge back in 2007. This is a picture of that car. I'm not going to show a video. You've all seen autonomous cars probably in real life. And we actually retired this car. We don't use it anymore. But we still think about what the world would look like when all the cars on the road are autonomous. Would we still need traffic signals and stop signs? Or would we be able to have intersections that look a little more like this? And what's going on here is the cars that are white have already called ahead to a program at the intersection with a reservation to get through the intersection. And the ones that are yellow don't have a reservation yet, so they have to stop. And there's a multi-agent algorithm that guarantees that there won't be any collisions as long as the cars follow the protocol, in the same way that there's no collisions when people follow stopping at a red light and going at a green light. And so the first time I showed this video, actually, it was at a conference in India, and people said that's what all the intersections look like here. But the difference is that we can guarantee that there aren't any collisions at these intersections. So this was again something that we started doing many years ago, and it's led to many years of research on what happens when if you have some human drivers in the loop, or if it's more multiple intersections, or if there's pedestrians or bicyclists. There's all kinds of questions that come up. But I think using AI technologies with autonomous driving, we should be able to get much more efficient use of our roadways, reduce travel times, reduce fuel usage and emissions. There's all kinds of advantages we could see. So let me so what I'm going to do for this talk, I'm going to talk a little bit about, because I advertised it in the title, I'll live up to the billing. I'll talk a little bit about robot soccer. I'm then going to teach you what reinforcement learning is. And then I'm going to go on to Gran Turismo, and where we've used reinforcement learning extensively. So in robot soccer, we have an ambitious goal. And by the way, the title of this talk was Humans versus AI, Robot Soccer in Gran Turismo. There have been a lot of domains where humans have competed against artificial intelligence. Back in 1998, a computer program known as Deep Blue beat Garry Kasparov, the world chess champion, at chess, and showed that computers are better than people now at chess. And that's happened in a number of other domains, including poker, including Jeopardy, including Go, and this is it's not all that AI works on, but it's sort of a good benchmark to see where are we in terms of humans. What can AI programs do better than people can? And there's many things that computers have been better at people than for many years, right? I would never want to. It's many decades now that I wouldn't want to get into an arithmetic competition with a computer, right? Computers are better than people at many things, but of course there's still many things that computers are not better than people at, and one of those is soccer. So we do have an ambitious goal, which is to build robots that can beat the World Cup champion on a real soccer field by the year 2050. So as you saw from that video, we're still a little ways away from that. But there's been a lot of progress. If you go to RoboCup, which is the Robot Soccer World Cup, it happens every year. Jay talked a little bit about it in the introduction. There's different leagues. There's some small robots that are working with a golf ball on a sort of a small field. There's some bigger robots that use a real soccer ball. There's some that are legged, that walk. There's a simulation league. And if you went to RoboCup the first years, it would have looked a lot like this. In 1997 and 98, the robots were barely moving. They were falling over. They were running into walls. Some of them actually caught fire. But they were working autonomously. They were sensing, deciding, and acting without a human in the loop. And that was a huge achievement back in the late 1990s. Most roboticists would work on only one part of the problem. They were roboticists working on how do you get a robot to walk, or how do you get a robot to see, or how do you get it to decide. We had the challenge of putting all those pieces together. And then if you jump forward just several years from there, but still almost 20 years ago now, you could see that there was really quick progress. In about 7 or 8 years, the robots were moving much more quickly. They were passing the ball sometimes. The bottom right corner was the first year of the humanoid competition, so there was just a penalty shot contest that year. But now since then, there are humanoid competitions. Here you'll see the goalie sort of trying to save the ball but missing. But But so there has been sort of progress as we go. And it's interesting. You can you want to hope when you've programmed both the attacker and the goalie, you don't really know who to hope for when they. But that video wasn't stopping. So 1 second. Okay. Good, and I said, and we have gotten to the point where some of the robots actually does make sense to have them play soccer against people. So every year we do take the champions of one of the leagues, that's called the middle-sized league, and have them play against people. And so here's me and some other of my colleagues, aging amateur soccer players, playing against the robots. And every year it gets a little bit harder. It's partly because the robots are getting better, partly because we're getting older, but one way or another, there's me scoring a goal, but I was called offside, so it didn't count. But oops. Sorry, I tried to kill the video and I killed the talk instead. So coming back again to here. So we are making progress, and so, who knows? Will we be able to beat World Cup champions on a real soccer field by the year 2050? There's still 25 years to go. We're still a long way to go, but 25 years is a long time. We'll see. We'll see. Yeah. So, by the way, there's a history in AI of predicting things too short, and so the first AI scientist predicted that it would be 10 years. They said in 1950 it would take about 10 years to beat people at chess. It would happen by 1960. It didn't happen until 1998. So we've learned from that, and we picked a year that's after most of us will have retired, and so it won't be nobody will hold us accountable. It'll be somebody else's fault if it's not met. But by the way, RoboCup isn't just about soccer. It's also there are other parts of RoboCup. There is a competition called RoboCup at Home, which is about building these sort of general purpose service robots that I told you about. So to do tasks like taking out the garbage, and so or putting away groceries, and so can we get a robot that can and interact with people in natural language, and maybe serve drinks to people, or to open the refrigerator. And so in Anahis Gym we have a mock apartment. We have robots like this one that are trying to get better at these sorts of tasks. And also at this is in a restaurant where the robot had to go and take orders from people in natural language and deliver the thing that they wanted to them. So these are all great challenge problems. And one of the sort of popular methods for trying to get robots to do these sorts of things is a type of machine learning that I introduced earlier. I mentioned it's called reinforcement learning. So I'm going to take a few minutes now to go into teaching mode a little bit and to help you understand exactly what reinforcement learning is. So first of all, it's a little bit like what it sounds. Reinforcement learning is sort of the way you would teach a dog new tricks or something like that. When it does a good thing, you give it some reward. When it does the wrong thing, you give it some punishment. There are different types of machine learning. The sort of most popular type of machine learning these days is something called supervised learning, and there are tools out there. Some of you may have used them, things like PyTorch or TensorFlow or other types of algorithms that you can just download and use or use online. And a pretty simple task is something like character recognition, like getting as input an image of a number and then being able to say this is a 4, or this is a 3, this is a 1. Supervised learning can do much more complicated things than this now. In computer vision, you can label where are the chairs and where are the people and what's going on the road, and autonomous cars are using it to label pedestrians and all kinds of tasks. But for autonomous agents, for things that have to sense, decide, and act, there's another type of machine learning known as reinforcement learning that's a little bit sort of more fitting. And the way reinforcement learning works is you have your agent that's trying to learn a policy, and a policy is a mapping from states to actions. So it's whatever state the world is in, the robot has to decide what to do. So the state could be, if you're an autonomous car, where you are on the road. If you're a chess-playing agent, what the board position is. And the action would be what you do next. You take that action, that changes to the next state, and you also get some reward, like good job or bad job. And that reward might come only at the end, after a long time. It might come that you only get reward after you win or lose the game of chess. And so there's a method, there's a sort of a formalism in AI called a Markov decision process. This is a picture of it. I'm going to give you a good flavor of how this works in a second. But there were some really exciting theoretical results in this area of reinforcement learning back in the late 1980s that proved that you could, through experience, an autonomous agent could learn the optimal thing to do. There's a very simple algorithm called Q-learning, then there have been a lot of improvements since then. But the real challenge, a lot of the challenge has been trying to get this to be useful in the real world. And so I'm going to show you especially an example of that at the end of the talk. But before I do that, I'm going to teach you what reinforcement learning is by asking you to be a reinforcement learning agent. So let's imagine here for a second that you, all of you collectively, are a single brain. You're a single decision maker. So that means I'm going to ask one of you at a time to represent the whole room, but you can help each other out and advise each other what action you're going to take. By the way, if you happen to have pencil and paper on you, you might want to take it out, or this might help. If you don't, that's okay. You can try to do it in your do this in your head. But what's going to happen is you as a group are going to act as a learning agent, and I'm going to tell you have 3 actions you can choose from. You can either wave, or you can stand, or you can clap. And I'm going to point at people, take turns. Maybe I'll start with some people in this section and this section. I'll give every section. It's a big room here, so not everyone's going to get a chance. But I'll give, ask one at a time to represent the group and do one of these things. Either wave, or stand up, or clap. Actually do it. Don't just say the word. I'm keeping you active here. Your observations are going to be colors and rewards. So it's going to look a little like this. Your color right now is green. You're going to tell me what action. You're going to see a new color, and I'll tell you some kind of reward that you get. And you're going to have to try to find an optimal policy. So what's a policy? Again, it's a way of selecting actions that gets you the most reward possible. Okay? Sounds sort of straightforward, right? So this is what a reinforcement learning agent could do, and I'm going to get you to try to understand reinforcement learning by being this reinforcement learning agent. So here we go. We're going to start with green, and we'll start here in the front. We get to wave, stand, or clap. So there is a wave, so I'll type a W here for wave, and you now see a red. You got a reward of 0, and the sum, I'll keep track of your sum of rewards as we go. Next. Clap. Blue with a reward of 0. Stand, okay. Purple with a reward of 0. Wave. Blue with a reward of 0. Let's go there. Another wave. Oh, okay. Blue again, but with a reward of -1. Stand. Purple with a reward of 0. Stand. Blue with a reward of 0. Wave, stand, or clap. Wave. Purple with a reward of 0. Stand. Blue with a reward of 0. Clap. Brown with a reward of 0. Let's go to the next section. We've been getting a lot of zeros. Let's see if this section can do better. So how about you? Okay, clap. Oh, cyan with a reward of 1. Okay. Wave. Yellow with a reward of 0. Clap. Green with a reward of 10. All right, how about over here?
It's one or the other. It's not a combination.
Wave, stand, or clap, one or the other. Clap. You can advise each other, by the way. Purple with a reward of 0. Wave. Blue with a reward of 0. Let's go back over here. Your turn. Stand. Purple with a reward of 0. Wave. Blue with a reward of 0. Clap. Brown with a reward of 0. Clap. Pink with a reward of 2. Now what? Clap. Pink with a reward of -1. Clap. Pink with a reward of -1 again. Stand. Yellow with a reward of 0. Any advice here? Wave. Pink with a reward of -1. Clap. Pink with a reward of -1. Clap again. Pink with a reward of -1. We're losing our reward. Stand. Yellow with a reward of 0. Any advice on yellow? Let's change sections. Let's go to this section. First in the corner. Yeah, go ahead. Wave. Okay. Pink with a reward of -1. Yeah. Clap. Pink with a reward of -1. Keep. Wave. Pink with a reward of -1. Stand. Yellow with a reward of 0. I'm hearing a lot of advice here. What's going on? I saw a clap. Green with a reward of 10. All right, next. Yeah, go ahead. Who's going? All right, clap. Purple with a reward of 0. Wave. Blue with a reward of 0. Who's next? Stand. Purple with a reward of 0. Stand. Blue with a reward of 0. Who's going next? Stand. Blue with a reward of -1. Next. Clap. Brown with a reward of 0. Okay, I got 2 more sections. Let's go to this section. Front in the green on the front here. Clap. Cyan with a reward of 1. What should we do next? Stand. Cyan with a reward of -1. Wave. Yellow with a reward of 0. Any advice? Clap. Green with a reward of 10. All right, clap. Purple with a reward of 0. Next. Wave. Blue with a reward of 0. Clap. Brown with a reward of 0. Stand. White with a reward of 0. Is that the first time we've seen white? Maybe. Clap. Yellow with a reward of -3. Stand. Pink with a reward of -1. Clap. Pink still with a reward of -1. Stand. Yellow with a reward of 0. What next? He doesn't follow the advice and goes with the stand. I think everybody was clapping, right? Cyan with a reward of -1. Wave. Yellow with a reward of 0. Clap. Green with a reward of 10. All right, last section. Let's go over to this section. We'll start over here in the blue on the corner. Wave. Red with a reward of 0. Clap. Blue with a reward of 0. Wave. Blue with a reward of -1. Next. Wave. Blue with a reward of -1. Okay, I saw a stand. Purple with a reward of 0. Who wants to go next? Okay, I see a wave. Blue with a reward of 0. Clap. Brown with a reward of 0. I see a stand in the back there. So let's see. White with a reward of 0. Now what? I saw a stand. Brown with a reward of 0. A wave. White with a reward of 0. Another wave. Brown with a reward of 0. I see a bunch of clapping. Pink with a reward of 2. What are we doing next? Wave. Pink with a reward of -1. Oh, a stand. Yellow with a reward of 0. Clap. Green with a reward of 10. All right. Good. So you just did some reinforcement learning. Did it feel like you were learning? You've got a reward of 36. You've done better than randomly. At the beginning, you didn't really know what to do at all. And I think there's at least some things you were doing. Like, for instance, what do you do when the world's yellow? Clap. So you learned something, right? Now, how many people know how to get to yellow? No, it's a little hard, right? So that if you were writing things down, and if we did this for long enough, you might have been able to figure out what you were doing, and you might have figured out how this environment worked. And so if we had more time, if we were in a class, I might now ask you how you did this. I want to get to some other things. So, but you were probably, finding patterns. And I'm going to tell you what the world looked like as you were going. What is your policy? Well, your policy was definitely to clap when you saw yellow. There were some other things you were doing. What does the world look like? What actually was going on was that the world looked like this. So every time there were 12 states, and every time you clapped, you moved to the right. Every time you stood, you moved up. Every time you waved, you moved down. There were some rewards. When you bumped into the wall, you got a -1 and stayed put. It was tricky because there were 2 states that were blue and 2 that were brown. You could get the +2 here with the pink and then stand, and then every time you did a yellow, you got a +10 and went back to the green. If we did this long enough, you might have been able to sort of figure this out a little bit and learn what was going on. So what was happening, we could formalize what just happened, and I'm going to go through this a little quickly, but there were some things you knew, and there were some things you were trying to learn as a reinforcement learning agent. You knew that your observations were blue, red, green, and black colors. You knew that there were rewards that were real numbers. They were integers in this case. You had 3 actions. And you knew that the world would proceed as you get an observation, take an action, get a reward, and so on. And there were some unknowns. You didn't know that the world was a 4x3 grid, and that there was a function that I was using that mapped your state and your action to a reward. And I showed you what that was. And there was a transition function that said when you were in a state, an observation function that said when you were in a state, what would the color look like, right? Where in the grid, some places were blue, some were pink. And then there was a transition function where, based on your state and your action, it took you to another state. And if you had figured all those out, then you would have been able to work on this whole sequence of state, observation, action, reward, and so on. And where the observation is all of these are computed by these functions here that you were basically trying to build a model of. And in the end, if you kept going, you'd be able to probably find an optimal policy, one that would clap and then wave and then clap and then stand and then repeat, right? So that's what reinforcement learning is about. So I'm now going to show you an example of where reinforcement learning can be used in a real application, a lot more complicated than those 12 states. And in particular, it's within this sort of my research problem slide, it's another problem that's been inspiring my research, and it's Gran Turismo. So that was also in the title of this talk. And this is some work that I've been doing with my group at Sony AI. We had a paper recently called Outracing Champion Gran Turismo Drivers with Deep Reinforcement Learning. It's the work of a large group of people. It's not, and all the work I've showed you is work of a large group of people. About 2 years ago, we had an article that was featured on the cover of Nature because we created a reinforcement learning agent that was able to race faster, to drive faster than the best human drivers at Gran Turismo. So I've already talked about computers being better than people at chess and Go, and we're trying for soccer. This was the first time that it was done for a real-time control task, not a turn-taking task like chess and Go, but one where you have to control the car in real time, 10 times a second. And so, and just like those other ones, the success of doing this relied on having a lot of computation and a lot of engineering to make things happen, and then and the ability to get lots of data, and then a few algorithmic innovations, nuggets that made it so that we could go beyond what others had been able to do. In all the videos I'm going to show you coming up, the white cars are going to be driven by people, and the colored cars, yellow and other colors, are driven by a reinforcement learning agent. And we call that agent GT Sophie. So first of all, Gran Turismo is a driving simulator, but it's a very realistic driving simulator. They call it the real driving simulator. You may have seen there's a movie out right now about somebody who learned to do race car driving in Gran Turismo and then went on to become a professional race car driver based on that experience. And it's used as an esports platform. It's used by professional. There are It's used by professional drivers to train, and there are generally people who have put in their 10,000 hours of training to become real experts at this task, and you'll see some of them later. It does model aerodynamics and tire traction and friction. And so what it looks like is this. This is a video of actually an all-human race but it's fairly photorealistic. It looks a lot like like a real race car, like a real race on a course. And the cars the tracks are based on real tracks. The cars are based on real cars. So we staged an event where we identified 4 of the top top drivers at this task. This was during COVID, so we couldn't draw from internationally, but it happened that 4 of the best drivers were from Japan, and so these are them here. And we challenged them to a race of 3 different cars on 3 different tracks, one of them being the Cirque du Lassart. If you're a Formula One fan, you know that's where the 24-hour Le Mans happens. And we challenged we put 4 GT Sophie agents against the 4 humans on the racetrack. In July 2021, we challenged them and actually lost in a close match, but the humans won that one. Then we went back to the drawing board, tried again in October, and won. And so I'm going to tell you about that process over the next few minutes. But first of all, the approach that we took was there were sort of 3 main challenges that we had to solve. One was race car control, just getting a car to drive right at the edge of the limit of its ability. That if it went a little bit slower, people would be able to pass by it. If it went a little bit faster, it would spin out and lose traction and not be able to complete the race. So being able to figure that out was a challenge, even on an empty track. But then when you put other people and other cars on the track with it, it gets even more challenging. That's the tactics part. When do you pass? When do you defend? And then there's this real interesting challenge in race car driving that I didn't know about before we did this on etiquette. That there's these sort of unwritten rules of what's sportsmanlike, what's fair and what's not fair. You can't push other cars off the track and things like that. And so we had to get the car to learn that as well. But fundamentally, what our car was doing was exactly what you were just doing. It was learning from scratch using reinforcement learning, to the point where at the beginning of learning, it was acting randomly, just like you did. You didn't know what wave, clap, and stand meant, so at the beginning, the car was just acting randomly, and as you might imagine, that caused it to sometimes go backwards and sometimes to run into walls and run off the track. It didn't look very good. But we gave it a reward of, positive reward every time it moved along the track, and the faster it went, the more reward we gave it. And just like you learned to clap when you saw yellow, it learned to go faster and faster. And it took about a day of training to get to be faster than people on an empty track, about a week of learning to be able to do it better than people in a crowded track, using pretty much the same process you just did when you were a reinforcement learning agent. So to give you a little more details, the actions of the car are it had to just either decide how much to brake or press the throttle. So that was just one number between -1 and 1. There's also another number to turn either all the way to the left or all the way to the right or somewhere in between. So it's just 2 continuous numbers that were the outputs of the car. And then the rewards were how far it's gone along the course. And then there were penalties for going off the course or hitting a wall or the tires slipping. And then at any state, rather than getting a color like you did, the car would get information about how fast it's going or how much it's accelerating or the roll, pitch, and yaw of the car, or how much load was on the tires, and things like that. And it also got some features of the track. So like, what's the shape of the upcoming track? And so for instance, here, as this car is driving, it would be seeing points on the left, center, and right of the track corresponding to what's the upcoming shape. So that would allow it to sort of predict where it was going. And we also gave it exactly where it was on the track as just a number from 0 to 1, how far it had finished it, because we were allowing the car to specialize its control for each car and track combination in the same way people do when they practice on a track. And then for the learning, we used a lot of computing. So just like large language models are trained with lots of GPUs. These were trained with a lot of PlayStations, Sony PlayStations. So we were partnering with the PlayStation group at Sony There are things called rollout workers that are basically just getting experience, just just like you were getting experience with wave standing and clapping, they were just practicing and figuring out what to do, and then seeing when they're in a state and they take an action, what would happen. And then there was all of that experience gets collected in what's called an experience replay buffer. If those of you with paper and pencil, we're basically collecting that experience replay buffer. And then we invented a new algorithm that's based on other existing reinforcement learning algorithms, but is essentially what's known as an actor-critic method. It was both learning a policy and an estimate of how good that policy was. I don't have time to go into the details of this. Those of you who are interested in the technical details can go to the Nature paper. But QRSAC was an algorithm called quantile regression soft actor critic. It was built based on an existing algorithm called soft actor critic, but it's basically learning a distributional reward function. So it's not learning just how good the action is, but it's learning a whole probability distribution over when I take an action, what's the likelihood something bad will happen or something good will happen. And it's underlying it was a neural network. And you may have been learning about neural networks in the news, but basically the neural network would take in a representation of the state, the car's velocity, acceleration, tire load, track features, and it would have to output how much it should accelerate or brake and how much it should turn left or right, and also how good that current policy is. And there's a lot of details here on this slide for those of you who are in the know, but it's a fairly standard compute architecture, but it's using a lot of computation. So here's some videos of what it looks like. After 1 hour of learning, you'll see that the car is not doing so well. It's sort of wobbling around a bit. But after 4 hours of learning, it's getting a little bit better. After 8 hours of learning, it's going fairly smoothly. I think I can. I don't know why the sound's not coming out of these now. It was before. That's strange. Anyway, we can do without the sound. And the final one in the bottom right here is faster than the best people. And I'll show you a little bit to what extent. So this is a histogram of the fastest recorded times that people have driven in one of those 3 car track combinations. So to the left is faster times. This is seconds. And these, each one of this is of the 100 recorded on a website called Kudos Prime. It's the best recorded times of people, and this is how fast the GT Sophie could drive after 4 hours, 8 hours, or 24 hours of training. So it's faster than almost all of the human drivers by 24 hours of training. And if we took the fastest human driver, that's the one shown here, its average time, and plotted it against the 100 laps of GT Sophie, we see that they're at about the same average time. And the second, third, fourth, and fifth fastest people, GT Sophie's much faster than. And in the other car tracks combos, GT Sophie's significantly faster than all the people. But being faster on an empty track wasn't enough. So we also had to deal with tactics. We had to then expand the state representation to let GT Sophie know where the other cars were. And we had to give it passing rewards. And we had to give it experience with other cars nearby. And so to put into that experience replay buffer I told you about, we would start it with 1 car in front of it, or 2 cars in front of it, or 3 cars in front of it. And we gave it situations that are important to learn. So we put it like, there's something called a slipstream pass, where a car goes like the same thing if you're riding a bicycle and you're basically drafting. It's behind another car where the air resistance is lower, so it can get some momentum, and then it jumps out and passes the other car. We wanted our car to be able to learn that and to do things like crossover passes as shown here. And so we curated the experience that the car had to get, and then put that into an experience replay buffer. I'm going to skip some of the details here. Oops, why is this? It's not in full screen mode anymore. Well, I'm going to just go with it. Maybe that's why the sound wasn't happening. But here's an example of defense. Oh, here we go. So you see GT Sophie's keeping the humans behind it by trying to not leave an opportunity to pass. And so that's one of the skills it learned. And here's that double crossover pass. So they're behind the people, and then after this corner, you see the two GT Sophie agents in front of the people. Right? So that was a tricky maneuver that it had to learn how to do. And so so that's another thing. We had to give these tactics. And then the last thing was this etiquette aspect. And the rules of racing have this sort of imprecision. It's like you have to, you get penalized if there's an incident that's your fault. And that, if it caused an avoidable collision or forced a driver off the track, these are all sort of judgment calls. And there's a human steward who makes the call whether these have happened. And so, you need the GT Sophie to be able to balance etiquette with assertiveness. So here's a car that's too timid. You'll see GT Sophie's in the lead here, but the person, the GT Sophie ends up getting scared in some sense. It gets close to the person, puts on the brakes. Here you see what it looks like when the person is driving in the console on the left there. And the announcer thought there was no way that the person would be able to pass GT Sophie, but it turned out GT Sophie got too timid, put on the brakes, and the person was able to pass. So that was an example of being too timid. It's one of the reasons we didn't win in the first attempt. But of course, you could also be too aggressive. So here's something that you're not allowed to do. So that would be judged as unfair. You can't just push the other car off the track. So we had to figure out ways to make to add in rewards to sort of penalize GT Sophie for doing things that it's not allowed to do. And then there's this additional aspect where we had to then pick one. We were training lots of different versions of GT Sophie, but we had to pick one to race against the people. And so we created sort of a battery of tests and to make sure it's good at the things it needs to be good at, and it's not too aggressive and not too timid. We had people race against them, and then finally picked the one that we would race against. And the first time we did it, like I said, in July, we raced on 3 different courses. And the way it worked was you got 10 points if you finished first place, 8 points for second, 6 for third, and then 5, 4, 3, 2, 1. And so the humans beat GT Sophie 23-16 on one, 24-15 on another. Start, we doubled the points because it's a longer race. And the people ended up beating GT Sophie by 86-70. And so, of course, we asked for a rematch. And so we went back for a few more months. We identified the things that didn't go well. In the interest of time, I'm not going to go into a lot of detail on this. It's in the Nature article again. We did improve the opponents that we trained against. And in the end, in the rematch, GT Sophie won 104-52, finishing first and second place in all 3 of the races. And then reporting on this is what was on the cover of Nature about 2 years ago. And I won't show this video. I've shown you a few videos already of it, but I will show you then some testimonials. So this is Emily Jones. She's one of the best GT Sophie drivers, one of the best Gran Turismo drivers. You can read some quotes from the others on here, but listen to Emily's experience.
It was really interesting seeing the line where the AI would go. So there were certain corners that I was going out wide and then cutting back in, and the AI was going in the whole way around. So I learned a lot about the line, and also knowing what to prioritize. Like the AI, in just turn 1, for example, I was braking later than the AI, but the AI was getting much better access to me and beat me to the next corner. So I just noticed that until I saw the AI, and I was like, oh, okay, cool. I should do that.
So she's learning from what GT Sophie was doing, and so now drivers are changing the way they drive based on what GT Sophie did. So we've now put this into the video game. There was a small trial run in February of 2023, and then we did make a permanent deployment in November of 2023. So now if you have a PlayStation and you have Gran Turismo, you can race against GT Sophie. It can control 340 different cars and lots of different types of tires on a bunch of different tracks. So now it's generalizing. It's learning not just on single track combinations, but it's learning policies that work with multiple cars and multiple tracks. And it's gotten a lot of really good reviews. Things like written here, that we've come away impressed with the human-like behavior of the new AI. Hopefully future game updates will expand its availability track by track. And a lot of other, just in the sort of the game magazines. And by the way, if you don't know, computer gaming is a 10 times bigger entertainment industry than the movie industry. This is a huge global market, and this is, as far as I know, the biggest commercial deployment of a reinforcement learning agent ever. There's hundreds of thousands of people racing against GT Sophie on a daily basis. So I'm going to take time for questions in a minute, but just telling you, we're not done. There's still more to do, even in Gran Turismo, and now we're also working on applying reinforcement learning to other games as well. But we're trying to work on tire wear and pit strategies. When should the car go into the pits to do changes? More strategic decision making and opponent modeling. Trying to be a good teacher or trainer of human drivers. And then also what we call driving with style. And so one thing we tried is we gave the agent a little extra reward for what's called drifting, which means sort of slamming on the brakes and skidding. And when we did that, the car learned to do this to go around the corner, which a person never would have done. So that was, we call that driving with style. So again, this was work of many different people. We do, the theme of Sony AI is trying to use artificial intelligence to enhance people's creativity, and we're working on other projects beyond video games there. But what I wanted to show you, today was how we've used this to beat the best people, to demonstrate that AI agents, and especially in particular deep reinforcement learning agents, which you now know what it is because you've been a reinforcement learning agent. This type of algorithm can race Gran Turismo cars better than the best people. So with that, I'll just remind you my research problem here, and I do want to say, where are we now? There's still, for me, as a professor here at UT, there's still lots of open research challenges to try to get at the nature of intelligence and to try to get at understanding how do we build intelligent artifacts. I am a professor here. I'm a part of the machine learning lab in Good Systems and the director of Texas Robotics and executive director of Sony AI America. You especially, there's a lot of, there's many children in the audience, there's students in the audience. For those of you, you still have lots of choices and opportunities. You can still decide, are you going to go to college? Where are you going to go to college? What will you study? What will your lifelong challenge be? My lifelong challenge has been to try to get autonomous agents to be robust in the real world. But there's others, and you have the chance to think about that now. Here at UT, there's many opportunities. We have a great program in computer science. We have an honors program called Turing Scholars. There's a freshman research initiative that allows undergraduates to get involved in research right from the beginning. And there's now a minor in robotics, in Texas Robotics. And then where are we with artificial intelligence? I just want to take one slide to step back and tell you it's a thriving area. There's lots of progress beyond what I've shared with you today. Many of you know about the great progress in language modeling and computer vision and things like this. But there also are some concerns, and I think it is incumbent on me, as especially as a member of our Good Systems Initiative, to ask the question a little bit: if we create robust, fully autonomous agents in the real world, what happens when or if we achieve this goal? Those of you who are closer to my age, know that there's many people who have envisioned a utopian society because of AI, like the Jetsons and Rosie the robot that'll do everything for you. And that's one possibility. Another possibility is there's been a lot of science fiction on the sort of negative dystopian outcomes like Terminator and RoboCop and things like that. But the question I would like you to ask is, on balance, the answer is somewhere in the middle, right? There's both benefits from artificial intelligence and there are challenges. I'd like you to ask, when would you have rather have been born? Would you have rather been born 50 years earlier than you were or 50 years after you were born? Do you think the world's getting better or do you think the world's getting worse? This is not actually a trivial question. The world is getting, there are new challenges in the world that didn't exist 50 years ago. The world's changing in many ways for the worse, but I think it's also changing for many ways in the better, and I think artificial intelligence can be part of the solution. And that's why I'm doing what I'm doing. That's one of the reasons I'm doing what I'm doing, in addition to trying to get at this question, what's the nature of intelligence? So with that, I thank you for your attention, and I'll be happy to take questions. Thanks.
All right, remember, right after the Q&A, we'll be wrapping up awesome door prizes. All right, so if you have a question, please raise your hand. I'll try to get to you with the mic, but if you come out to the aisle, that will help. You can shout it out. If we could have everyone be quiet so we can hear your questions, and if you could shout it out, even better. So, yeah, just stand up if you have a question. I'll try to get to you, but shout it out from your seat.
Hi. How do the rewards work? Like, for a child, they know they like to read, and so what does the computer like?
Yeah, so the question was, how do the rewards work, right? You know, for people, the rewards are like a sugary treat, or for dogs, it's a biscuit, or something like that. So it's just like the stand, wave, and clap exercise I gave you. We tell the computer that we want it to come up with a policy that gets the highest reward possible. So we basically tell it that, you know, the more positive numbers they get, the happier it should be in some sense. And so now then the question is, how do we decide what should we reward it for? And that's actually a very tricky and deep question, and I do a lot of research on that in my lab, is how do you come up with what's the right reward signal, right? If we just told GT Sophie, you get a plus 100 when you win the race, and you get a minus 100 when you lose the race, it never would have learned a thing. We needed to give it rewards and penalties for various things along the way. And so that's you know, sort of the reward engineering problem is difficult. But what it should, but in terms of like, you know, what it's incentivized to do, the program is designed to take actions that it predicts will give high rewards. Just like you were trying to take actions that would give you a high reward in the exercise I presented. That's a good question.
Hi, you mentioned like a bit of collaboration between robots and AI and like in the software program. How exactly does the process of like teaching that like change when you have to get like two AIs to collaborate?
Yeah, so that's a great question as well. That's the essence of multi-agent systems or multi-agent learning. And there's people write PhD dissertations on how to do this. There's fields of mathematics known as game theory that answer some of these questions of how can you get agents to collaborate. The simplest thing is to just let each of the agents get its own reward signal, and they get a positive when something good happens as a team. But that's going to lead to slow learning, and so we could do a whole course or a whole lecture on the ways that you have to learn when there's other learning agents at the same time. But it definitely makes it difficult. One of the reasons that you could learn this task of wave standing and clapping was because the world wasn't changing. It was always the case that when it was yellow and you clapped, you got plus 10. If the world were changing while you were learning, it would be even more difficult. And when there are multiple agents learning, the world is changing because they're learning at the same time. And so this makes it, this is some of the trickiness of it. So if you want to get a deeper answer, there's plenty of papers on my website that go into it in detail, but that's the best I can do in this time.
If there is a sort of a Moore's law equivalent to the AI growth, how do you think it's going to be?
So the question is there a Moore's law equivalent for AI growth? So for those of you who don't know, Moore's law is this sort of empirical or sort of phenomenon that's happened through computer science that every 18 months or so, traditionally, we've been able to get twice as much computing for the same price. And that's driven a lot of the progress in computer science, and that the iPhones in your pocket now are a lot more powerful than the ones that you had 10 years ago, and the computers on your desks are more powerful. So artificial intelligence doesn't have sort of exactly the same kind of notion. AI is one of the ways I see AI is trying to get computers to do the things you can't do with just brute force computation. And so we're always trying to get computers to be pushed beyond what you can do by just relying on Moore's law. Moore's law, of course, is getting more difficult to keep going because it's getting harder and harder or more and more expensive. But computation still is sort of accelerating. AI, some of the things come for free. Some of the things in AI come for free with more computation. But to me, the interesting aspects or the algorithms are the ones where we're taking the best computation we have today and going beyond what you can do with brute force, and that just that keeps changing as Moore's law continues. So I don't know if that answers your question exactly, but I don't think anybody's characterized sort of an AI equivalent.
Thank you. Can AI solve the traveling sales rep problem? Assuming it hasn't, and is it solvable by AI?
So the traveling salesman's problem, for those of you who don't know, is a problem where you have a bunch of different cities, and a salesman has to go to all of those cities in the shortest path possible. And there's a result in theoretical computer science that this problem is it's NP complete. It means that it's combinatorially difficult. That basically, even if you had infinite computing power, if you make the problem bigger and bigger, it's going to sort of exceed your computing ability. And so there's theoretical results that unless P equals NP, which is still an open question, that the answer is no, that you would not be able to come up with an efficient algorithm to solve the traveling sales problem optimally, no matter how much computing power you had. Now, artificial intelligence programs can approximate solutions in various situations, and and for realistic sizes, you can solve you can come up with good solutions to the traveling salesman problem. But does AI break through the theoretical results from theoretical computer science? No, they still hold.
You talked about if you just gave a 100-point reward for winning, 100 for losing, that wouldn't be effective. You've got to come up with good strategies. And is that just a computational limitation? Like if you had like it would take too long to learn that way, but if you had more computer power.
Yeah, that's a great question.
Do you think that it would come up with better rewards than you can eventually and come up with a better algorithm?
Yeah, and so that's a great question. In theory, yes. In theory, if you had enough computation and you just gave the reward for winning and losing, a straightforward reinforcement learning algorithm with infinite data and infinite time would come up with the optimal policy without those extra rewards. And in fact, if you followed the sort of Go results from DeepMind, they first came up with AlphaGo, and then they came up with AlphaZero, where they gave less information, and their conclusion was that the information that the humans gave were sort of holding it back. It was making it learn more quickly, but putting a limit on what it could learn in the end. And I think, yes, it's possible that the rewards we're giving are making it so that it's learning more quickly, but it's sort of cutting some corners. In the same way, if you were playing chess, you really care about winning, but you might give a reward of plus 50 for capturing the opponent queen. That could cause you to take a move that captures the queen and puts yourself in danger, right? So if you get the rewards wrong, you can mess up the policy. There are some theoretical results. There's types of shaping rewards, they're called, based on potential functions that don't change the ordering of the policies. But in general, it is risky to put in these intermediate rewards and can make it so that you learn something suboptimal. So that's a very good point.
If AI gets more intelligent than you, would it be hard for you to understand what it's doing?
Yeah, that's a fantastic question. In fact, it already is. Some of the things that artificial intelligence programs are doing, we don't understand how they're doing it and why they're doing it. When they use a neural network, it's we can see what the input is and what the output is, but we don't necessarily know how it's working on the inside. Think about it though, I'm doing things, you're doing things, and I don't know exactly how your brain works. right? I can't really see inside your brain. I don't know what you're thinking, but I still see you doing things, and I can sort of explain a little bit about what you're doing based on watching you. And you can sort of understand what I'm doing by watching me, even though you don't see exactly what's going on in my brain. It's sort of like that for these intelligent artificial intelligence programs as well. We can see that they're doing smart things, and we know more about how they work than we know about the human brain. We can look and see what the numbers are doing inside, but we can't often explain how they're doing it, and you're right, it becomes very difficult for us to understand. So that's one of the ways we try to learn about intelligence, by building intelligence things, machines, because now we can try to inspect them and try to figure out what's going on and how they're doing smart things. So that would be a great question for you to try to work on if you're curious about it. There's no real good answer for it. Thank you.
You just got invited to submit an application to describe your All right, we have time for one more question.
So my question is, what happens with all of the data? Right now it's probably manageable, but it becomes less and less manageable the more this grows. You start getting massive amounts of data, and then in addition to that, how do we keep up with that data as humans? Because as she just asked, how do we know what's going on? So what happens to all the data? How do we as humans keep up with that data as it continues to grow?
Yeah, I mean the sort of the current boom and acceleration in artificial intelligence is a sort of a result of some algorithms, some computation, and some data, just massive amounts of data. So there's training data that goes in, like language models are trained on all of the language that's out there on the internet, and then there's data that the algorithms produce. And when autonomous cars are driving around, there's all kinds of logs that are stored of where have they gone and what have they done. And when the robot soccer players are playing, we store the data. And basically, right now the data is being produced more quickly than we can analyze it, but it's there. A lot of it's being stored. At some point, it's too much to store, so we have to decide what to throw out. But the data is a valuable resource. It's something to learn from. When a computer makes a mistake, we can go back and try to look through the data to try to explain why it made the mistake and improve the algorithms from it. I'm not. The easiest way to deal with overwhelming data is just delete the stuff that you don't need, right? I mean, eventually we can't store all of it that's there, but it becomes a question of what's the judicious storage strategy, and
You cut it off at a certain point. You take out like some of the initial learning.
sometimes, yeah, like sometimes when we know what it's like, when we're training GT Sophie runs. When we're first learning, we store everything and analyze it. Once we sort of know what we're doing, we might try to reclaim some of our disk space and say that old data is not going to be useful anymore. Sometimes you archive it and put it on hard disks and stuff like that. But that's always a data management strategy is always sort of something you need to work on. Thanks.
We're going to do our prize raffle now. In order to thank Dr. Stone, you have a choice. Wave, clap, or stand.